So we are going to see, we have been had a, what I should say, we were having a general recourse into how the role of information and probability distributions in to pinning out the probabilities, whether they were conditional or marginal. So in the same theme, we are going to see because in the previous thing we took the relations, the correlations between certain range of values. But in principles, they could be those random variables can have arbitrary, they can take arbitrary values. So, and in this context, we have to see whether we can generalize these properties of and further properties of correlation. So, because, for example, we can generalize correlation, those generalized set of joint probability distributions. So here we have to see something called, a word called refinement. Refinement. Refinement in the context of, for example, if there is a sample space and there are we have to pin down what's the probability of a given thing. In case of marginal distribution, we are not interested in the rest of the ensemble, which or the sample space which may be constructed out of which may take those ensembles into or relative subsystems into consideration. The point is, if in case of conditional probability distributions, if if there is a certain variable random which is related to another variable, so the measurement of that variable, if it's dependent upon having some property which is dependent upon other variable in that subsystem, so in that subsystem, the value of this parameter, which is somewhat related to other parameter, so its value will be same, irrespective of whether the other parameters or other variables are changing or they remain constant. So the thing is that we can say that an event xi, which is disjunction of several exclusive events so that xi occurs if any of occurs. That means that xi occurs if any of xu occurs. So in that random subsystem where mu can take any values 1, 2, 3. So if a particular event which occurs, it's oblivious or independent of the other thing. So it is actually the failure to distinguish or failure to distinguish between different axes. So this probability distribution which distinguish between this probability distribution which distinguish between this and the rest of it, it's called refinement. It's called refinement. The so this refinement is the ability to failure to distinguish the different these measurements. Whether the measurement of an event is not conditional to the measurement of the other events or distributions. So in general, we can say a distribution P prime is a refinement of P if P of xi yj is probability of yj for all I goes to j. Now there is a theorem which says, the theorem says, so the theorem says that P prime is a refinement of P such that, so if there are original variables x, y and this prime, they shall be greater than or equivalent to x. So this means that probability shall never decrease upon refinement of distribution. So it means even though you are, since the main this thing, it's disjunction of the rest of the events in that sample space. So it doesn't mean that the probability should decrease in any sense of the word in that sense. So now we can take a joint probability distribution with, for example, a set x and y. We can have its x may be belonging to x1, x2, y may be. So we'll see how in a joint probability distribution this property of refinement it turns out. For example, so by the division of x's into finite intervals xi, yj, we arrive at joint probability distribution. Joint, this is finite joint distribution. Which can be this thing. And x belongs to xi and y belongs to yj, sorry. So we have to, the theorem should allow us to have a general correlation vis-a-vis these probability distributions and a sort of probability measure vis-a-vis both of them. For example, if we assume collection of arbitrary sets x, y, z with the probability measure of this x cross y cross z cross z on their Cartesian product, and q mu be the any finite partition chi into x I mu, and in the same way y may be equivalent to y mu j into subsets. So such that the subsets are x mu cross y mu j I j cross z mu k. So you can have another refinement of P in terms of x mu's, y mu's, such that the way this constraint was there, so it's always greater than this thing. And so from this you can say if you have sub partition of this thing, so this means that a refinement P mu is subset of P mu. And P nu may result in the subdivision of further subdivision of subsets x mu I cross x mu j cross so and x mu k or j z mu k. Yes. And this thing can be written as P mu is subset of P mu as P mu is x, y, z, P mu is greater than P mu. So the question is so now the question is the way in real analysis we have a idea of a bounded set which has a limit point. So in the same sense, can we have the idea of refinement which will pin down a given variable, its probability which is correlated with some another variable. So it's oblivious of the disjunction or the other sort of variables which may whose probability will not affect this variable. So the original thing, it's always less than the total number of this thing, the set. So if you want to write it in terms of this, if you want to write it as a definition, the definition goes like this, that if f exists and is equal to a for every epsilon greater than 0, there exists an a epsilon delta such that f of beta minus f a is less than epsilon, where beta belongs to delta and beta is less than or equivalent to a. So you can say from this the correlation of x, y, z and the refinement property is a monotone function, is a monotonic function on the directed set of partitions. directed set of partitions. Partitions means those sample space. There can be subspaces on those sample spaces, which is in turn the disjunction of the probability measures, which is interrelated to the original probability and its conditional relation to that probability in some particular variable, and which is oblivious of other partitions or sub other partitions. So monolithic function means, monotonic function means it preserves or reverses given order. So, so the mapping between the original probability measure and the correlation with regard to that distribution. So it not only preserves it, it also reverses it. You can go back and forth by some suitable mapping. And the same thing can be, what I should say, if we want to if you want to write it like this, so let be arbitrary sets with a probability measure on Cartesian product and let F be a 1-1 mapping. So you are trying to see how in a correlation a given probability distribution rank is related to the other part of that distribution, and the mapping can be 1-1 as well as it preserves or reverses the given order in that sense. So you can have how to show it's preserving 1-1 mapping. So the joint probability distribution from which we are seeing the joint probability distribution, which is over x cross y cross and z cross, leads to u cross v cross and so on and w. It's the induced probability on the product, this, yes, which measures a sort of image of this in that sense, which is the original measure. So now if we consider original set X and X, Y, Z, it can have subsets Xi, Yi, Yj, and Zk with probability distributions Pij, K is MP is the, what I should say, measure of this chi I cross Yj cross Zk. So there is a corresponding partition P prime such that of U and V and W into the image of the sets P, Ui, Vj and Wk, where Ui is a function of xi, Uj is function of Vj is g of yi, and Wk is a function of h times z of k. So you can say each element has some functionality from the original measure, probability measure, and to its to the correlation to that thing. That's one to one, and sometimes in the set theory of set language, you can say isomorphic. It's isomorphic. Yes. And cite that if you want to write it further, cite that. Cite that P is what? If you started P is the refinement of the distribution, which is such that P is Ijk is so that X, Y, Z, P is U, V, so on and P prime. So due to the correspondence you can have between P's and P, you can have a supremum of this can be X, Y, Z is equivalent to supremum of U, V, W, P prime. So it's like you can have this refinement of measurements. So you can now this entire thing can be crystallized or it can be stated as a part of theorem. How each the image, the refinement which we have defined in terms of correlation distribution, where we map two functions which are related conditionally. Their mapping being unique or one-to-one, and it's oblivious of the other, what I should say, it's oblivious of other samples or other, what I should say, subspaces or subsets or other distributions or other probabilities. It will not have effect on that thing. So if we are going to take portion of that subspace whose probability is somehow conditionally related with the portion of subspace which we are interested in, whose map is one-to-one and unique in these two images. So we can say that for X, Y, Z is basically U, V, where U, V and W or any one image of chi y, and z respectively. So in some sense, we can say this x, y, and z is equal to, so the functionality of x vis-a-vis x. This is g of y. This is h of z. This is the functionality of the functionality of this functionality of this for all one functions of x, y, and h of f, g, and h. So again, there can be another thing which you can say is that since we are basically interested in distributions, but there is the idea of joint probability distributions where there may be more than one or two random variables. So for a given joint distribution, for a pair of events, in space-time, the correlation is invariant to arbitrary space-time coordinate transformations. And again, in allowing different transformations for each coordinates of each event. So what it means that in a joint distribution for a pair of events in space-time, the correlation is for a pair of events, so how they are related. So it's exclusiveness or in disjunction to the other events. We are not bothered. We are bothered about the correlation between two distributions in a joint distribution for a pair of events in space-time. The correlation is invariant to arbitrary space-time coordinate transformations. So the transformations can be arbitrary. So the sort of variables which are related with regard to each other in whichever dimensions we can take. So that's, we have taken it from a to arbitrary space-time, under arbitrary space-time coordinate transform, even allowing different transformations for each coordinate of an event. So even though we can individually in that sample space allow for the parts of that sample space which are related with each other in their joint, even if there may be different transformations, it's not necessarily they will have same transformation. So it speaks something about the nature of what I should say intrinsic nature of how we define correlation, and correlation can be absolute rather than we can say it's relative. Is an absolute in the sense that we absolutely define the relation between two random variables which are related in a joint distribution where some conditional way, this probability distribution, only some. So we can describe, so it's not relative to the other parameters. Once we map a given sample space to another sample space where the part of sample space which is related to this space, So the part of sample space is oblivious or independent of its other larger thing. So that statement is absolute. So it's not related to the other parameters in the sample space from which we are basically interested in. So that way the statement is absolute. Correlation is absolute, not relative. Uh, in terms of the measured values. So random variables is completely independent of the scale of measurement for chosen for those variables. So we stop here, and in the next we are going to more information for more general distributions. We are going to continue. Thanks.